got there via highway. We are located about 4.5 hours driving time from the Columbia ice field. So we drove up there and took 4.5 hours. By going to the Canadian Rockies and filming some of these alpine glaciers, we can at least preserve their record on the face of the planet. Another reason that we'd like to go and take a look at these alpine glaciers is that glaciers have had a dramatic effect on the Canadian Cordillera. That's the western region of Canada, both from glacial erosion and glacial deposition. And by going there, we can see firsthand how some of these landforms are produced. Today, glacial ice covers about 10% of Earth's surface, while the vast majority of this ice, or about 97% of it, exists in the Antarctic and Greenland. There are still small alpine glaciers and ice fields in North America that do provide research opportunities for glaciologists, geomorphologists, and geologists. Today we've come to one of the largest ice fields outside of the Antarctic and Greenland. It's called the Columbia Ice Fields. This is in the heart of the Canadian Rocky Mountains and lies in a protected area of Jasper National Park, Alberta. This ice field is approximately 325 square kilometers, and several outlet and valley glaciers emanate from the ice fields. One in particular behind me is called the Athabasca Glacier. The Athabasca Glacier is approximately 6.5 kilometers from the beginning up in the ice field to its snout or toe right in behind me here. Glaciers have two distinct different zones on them. They have an accumulation zone in the upper part of the glacier and an ablation zone down in the lower part of the glacier. If you look into the upper reaches of the Athabasca Glacier up toward the top, what you see is pristine white snow. This is winter snow that has survived the summer melt season and is turning into firn. And that firn then will gradually turn to glacial ice. That area up in the accumulation zone there is also got what we call a positive net balance of ice. In other words, more ice is accumulating up there than is melting in the summer. But as we proceed to the lower part of the glacier, we get down into the ablation zone, and you can see that that's characterized by very dirty ice covered with a lot of sediment and other types of glacial debris. What we're seeing down in this zone is a negative net balance, which means that more ice is melting during the year that is flowing down from the top. And the marked boundary between the two zones, the accumulation zone and the ablation zone, is called the firn line. Formation of glacial ice is caused by two major factors. One, winter snowfall that can survive the summer melt season turns into a granular form of snow called firn, F-I-R-N. This firn that gradually coalesce into solid glacial ice. And this process will take approximately 15 years, but it depends on the local conditions. Another way we get glacial ice forming is that as summer proceeds, we get a lot of melting on the surface of the glacier. This water then percolates down through the internal parts of the glacier, refreezes, and reconstitutes into glacial ice. I'm standing here at the toe or the snout of the Athabasca Glacier, and it's a very good place to take a look at how glacial ice wastes away. And there are four main ways this occurs. The first way is through melting, obviously. We see a lot of meltwater around here. But specifically, we can get surface melting, and right in behind me, we can see a little surface stream flowing on top of the ice. Another way is just internally, in the middle of the ice. That ice can be above freezing and melt. And then the base of the glacier can be melting. And that happens because there's so much weight of ice on top of it that as we increase pressure, we increase the temperature. So typically, down around this area, this glacier is melting at the base as well. Now, another way that we can lose ice out here is through just chunks of ice breaking off. It's called calving. So we can get the calving of ice here. And you can see right here, there's a chunk of ice that's cracked here. This piece is getting ready to just fall down. And once it does that, it's detached from the glacier itself, it will melt even more quickly. Another way that we can lose ice volume out here is through wind deflation. What that means is that further up the glacier where there's still fresh snow lying, when a strong wind blows up, it will blow the snow off of the glacier. And this results in that snow not turning into glacial ice, and so we lose a little volume that way. And the fourth way that we have wastage on a glacier is through sublimation. Sublimation is where we have H2O go through a phase change directly from a solid to a gas, does not pass through the liquid phase. And one more aspect to the snout of a glacier that you might want to be aware of if you ever come out to a place like this is how soft the ground is. So if I walk across here, you can see how my feet go into the mud. Glacial ice flow characteristics are different at the surface. What happens on a glacier at the surface is that the ice is still very brittle, and as it flows over uneven surfaces, as you can see from this shot on the Athabasca Glacier, it will open up into crevasses. Now these crevasses generally don't go too far down into the ice, probably no more than about 30 or 40 meters. And the reason for that is, as we increase the depth of the ice, the overlying weight of the ice causes that ice further down to be a plastic, and it flows as a plastic, which means it will not be brittle and not open up crevasses. Glaciers transport a large amount of material, from tiny clay-sized particles to boulders that can be the size of small buildings. They're called erratics. And this material is carried in 3 different locations on the glacier. One, it can be carried on top of the glacier. We call this supraglacial. It can be carried within the ice. It's called N-glacial. And thirdly, material can be transported along the bottom or the base of a glacier, and we call this basal material. Off to my left here, we can see a feature called an ice-cored lateral moraine. You can see it's pretty obvious there's ice underneath it, but you see a very dark surface covering over it. That dark surface is silt, sand, boulder-sized particles, and you can see it gets fairly deep up along the top. That debris that lays over the top of this ice prevents it from melting very quickly, so it actually insulates it from the heat. And this area actually stands out as an ice core, and the ice is melting much more slowly than the glacier, the main glacier, off in that direction there. Now you can see this is a south-facing slope. The sun's just up behind me here. It's in and out of the cloud right now. But as the sun hits this dark surface, it's going to heat it up, and what we end up getting by afternoon time is a fairly constant rain of boulders melting and rolling down the slope. And as I'm going right here, one just fell in. There's fairly constantly these small cobbles and boulders coming in. You can see that probably a few days ago we had a relatively major collapse of some of the ice blocks in here, and then if you look over here, again in here, this is calving of ice here, and it brings down a fairly large rain of material as it comes down. Once this ice core is finished melting, it's simply going to form a lateral moraine like we've seen elsewhere in this area. Glaciers move a great deal of material, from the tiny silt-sized particles we see in suspension in this creek here to larger boulders you see here, and in fact they move great deals of material. We're going to walk up toward this very large feature here. This is called a lateral moraine. This particular lateral moraine was created by the Athabasca Glacier about 100 years ago when it was much further down the valley. So it's left all this material deposited. In addition to lateral moraines, if we look right down below us here, sometimes the glaciers just directly drop material down, and we refer to that as ground moraine. That as we move up through and approach the lateral moraine, you can look down and see various sizes of material. Glaciers work to erode material, and this is a really good example of it right here. I'm kneeling on a piece of bedrock that this glacier came across a few years ago, and when it did so, it had a rock and many rocks in its base, and as it moved across like that, it scratched. These scratches are what we call glacial striations in the rock. Now, Glacial striations are very good diagnostic features for determining what direction the glacier moved. And if you can take a look at these striations right here, you'll see that they line up directly behind me with the ice as it moved this way. This is awesome. If you take a look right over here, we see a beautiful little stream that's flowing on the surface of the ice. See it working its way down here, and then the meltwater coming into this larger little stream of meltwater. If you go back up on the ice and take a look at how the stream's working its way down, you can see it actually meanders, just like a stream would under typical fluvial processes. Eventually, when this bunch of ice here completely melts, there will be a little bit of sediment that stands out as a sinuous little ridge along the ground. So this is the beginnings of what we call an esker. I'm standing here at the precise headwaters of the Athabasca River. You can see the water melting out of the snout of the Athabasca Glacier. And then interesting things going on down here. We have in geomorphology, there's a distinct type of process known as glacial fluvial processes. That's where we have the glaciers depositing a lot of material on the ground and then reworked by running water, and that's called glacial fluvial. And one of the things you can also see in the water here is it contains a great deal of rock flour, the very fine sediment. So if we take a look at this, we can actually take a sample here. Let's get a little more here. And what we'll do is, you can see how cloudy this water is. What we're going to do is let it sit and see if we can get any of that sediment to settle out. As this water is flowing off of the snout of the Athabasca Glacier, it's calving little pieces of ice right here we can see in the water. And one of the things you can actually see in the ice here is you can see the very large crystals that occur. And what's happened is we started off as small snowflakes, went into fern, and now you can see this is just about solid ice, but it has maintained a crystalline structure. Walking along a glacial meltwater stream, this is issuing from a glacier just above me here. One of the first things you notice is that the water has a milky appearance. The reason for this is that the glacial ice comes down the mountain. It tends to grind the bedrock and pulverize it into a very fine silt. This silt is called rock flour, and it is so small it stays suspended in the water, giving it the milky appearance. After this creek flows into a lake, as it's heading down to right now, it typically gives that lake that distinguishing turquoise blue water that is so characteristic of these high Canadian alpine lakes. We've waited about an hour since we took this sample of water out of this meltwater stream, and if you can take a look at the bottom, what you can see here is look at the amount of sediment that's already spilled out of there. So this particular stream here is moving a significant amount of silt-sized sediment. The Athabasca River here starts flowing down this way. You can see it's beginning to rework the material that this ice-cored lateral moraine has dumped into the area. So what's going to happen now is this little river here is going to take and rework some of the boulder-sized sand and silt-sized particles and start moving that down the valley. When you see rivers like this moving this glacial material long distances down valley, we refer to that as valley train. And if you go out through the Athabasca River Valley, you'll see a considerable amount of valley train. I'm standing here on top of a terminal moraine built by the Athabasca Glacier in 1900. The Athabasca Glacier is currently behind me about 1.5 kilometers, which means it's retreated back 1.5 kilometers in 106 years. Terminal moraines are constructed by glaciers as they retreat back, and they stay in one position for a while. Now, the Athabasca Glacier probably remained in this position for a few years, thus depositing a fairly high and prominent terminal moraine. But we would find more as we move back toward the Athabasca Glacier. However, this particular moraine is the most prominent one. Out here doing this kind of filming, it can get hot, you know, and the guy gets kind of thirsty once in a while, so this is where we call on the other big force amongst our film crew. Catering! Thank you very much.